Science is built on a promise that with enough data, better tools, and deeper theories, every mystery can eventually be solved. This belief is rarely stated explicitly, but it sits beneath much of scientific culture. Problems are hard, not impossible. Ignorance is temporary, not fundamental. And yet, physics itself has reached a point where it openly admits something unsettling. There are problems that are not just unsolved, but unsolvable. Not because we lack intelligence or technology, but because the structure of reality places limits on what can be known. This admission changes science at a fundamental level. It forces a shift from unlimited optimism to disciplined humility. The first cracks appear when physics confronts self-reference. Systems that try to describe themselves run into unavoidable limits. This is not a philosophical opinion, it is a mathematical fact. Gödel's incompleteness theorems showed that any sufficiently powerful formal system contains true statements that cannot be proven within that system. Physics relies on mathematics. If mathematics has intrinsic limits, then any physical theory built on it inherits those limits. There will be truths about the universe that cannot be derived from the laws describing it. This is not a temporary gap. It is structural. The universe may contain facts that no theory can capture completely. Another unsolvable problem appears with prediction. Classical physics once suggested that perfect knowledge of the present would allow perfect prediction of the future. Quantum mechanics destroyed this idea. Uncertainty is not due to ignorance, it is fundamental. There are limits to how precisely certain properties can be known simultaneously. This is not a technological limitation. It is built into the fabric of reality. No future theory can remove it without contradicting observed facts. Some aspects of the future are not just unknown, they are unknowable in principle. Physics accepts this. It does not try to eliminate uncertainty, it incorporates it. A deeper unsolvability appears in the measurement problem. Quantum mechanics provides a rule for calculating probabilities, but it does not explain why a specific outcome occurs when a measurement is made. The theory predicts distributions, not events. Despite decades of work, no interpretation has resolved this fully without introducing new problems. Some interpretations multiply realities, others introduce observer dependence. Others add hidden variables that remain experimentally inaccessible. Physics admits that there may be no single answer to what really happens during measurement. The question itself may be ill-posed. This is not a failure of effort. It may be a boundary of explanation. Black holes introduce another unsolvable tension. According to known physics, information must be conserved. According to classical gravity, information can be lost. Reconciling these two principles has led to decades of paradoxes. While progress has been made, the complete picture remains elusive. More importantly, some physicists suspect that no single observer can ever access all the relevant information. Complementarity suggests that different descriptions are valid in different contexts, but cannot be unified into one global account. If that is true, then a single complete description of reality may be impossible even in principle. Reality may be consistent without being globally describable. Cosmology pushes unsolvability even further. Physics can describe the evolution of the universe once it exists. It cannot explain why the universe exists at all. It cannot explain why the laws are what they are, why the constants have their values, or why the initial conditions were set the way they were. These are not questions awaiting better telescopes. They are questions outside the explanatory reach of physics. Admitting this does not weaken science, it clarifies its domain. Science explains patterns within existence. It does not justify existence itself. Attempts to erase this boundary lead to confusion, not progress. There is also a computational limit. Some physical systems are so complex that predicting their behavior requires simulating them step by step. There is no shortcut. The universe itself must do the computation. This means that even if the laws are known, outcomes cannot always be predicted faster than they occur. In such cases, prediction is not just difficult, it is impossible in principle. The future cannot be compressed into a simpler description. This introduces a limit on knowledge that has nothing to do with ignorance. It is imposed by complexity itself. Physics also confronts undecidability. Certain questions about physical systems may be mathematically undecidable, meaning no algorithm can determine the answer in all cases. This is not speculation. It follows from the embedding of computation within physical law. If physical systems can implement arbitrary computation, then they inherit the limits of computation. Some questions about their behavior will have no general solution. Nature itself can pose questions that no theory can answer universally. This realization changes how science sees progress. Progress no longer means approaching total explanation. It means mapping what can be known and identifying what cannot. boundaries become as important as discoveries. Knowing that a problem is unsolvable prevents wasted effort and false expectations. It also reshapes interpretation. When physics admits a problem is unsolvable, it is not surrendering, it is refining its understanding of itself. This honesty is rare in human endeavors. Science is often portrayed as a path toward complete knowledge. Physics now reveals a different picture. Knowledge is powerful, but finite. Explanation is deep, but bounded. There are truths about the universe that cannot be packaged into laws, equations, or models accessible to us. This does not mean reality is irrational. It means rationality has limits, and those limits are part of reality. This realization has profound consequences. It undermines the idea that science will one day replace all other forms of inquiry. It also undermines the fear that science will drain the universe of mystery. Mystery does not disappear when explanation advances. It migrates. It moves to deeper layers. Physics has not eliminated mystery. It has discovered where mystery cannot be eliminated. This changes the culture of science. It encourages humility. It discourages overreach. It reframes unanswered questions not as failures, but as features of a world that resists total capture. The most important shift is psychological. Accepting unsolvability requires abandoning the belief that every why has an answer. Some questions may be meaningful without being answerable. Some truths may be real without being knowable. This is not pessimism, it is realism. Science does not lose power by recognizing its limits, it gains clarity. The admission that some problems are unsolvable does not end inquiry, it redirects it. Scientists focus on what can be learned, not on fantasies of total comprehension. This is a maturation of science, not a retreat. Physics admitting unsolvability changes science because it changes expectations. It tells us that the universe is not obligated to be fully transparent. It tells us that understanding is always partial. And it tells us that the goal of science is not omniscience, but coherence within limits. The deepest strength of physics may be its willingness to say, clearly and honestly, this is as far as explanation goes. Beyond this point, there is structure without derivation, fact without reason, reality without justification. Recognizing that boundary does not close the book on science. It tells us where the book ends, and knowing where it ends is itself a form of understanding. This is Veritas Labs, where truth is tested.